So in this video, I'm going to be showing you some of the equipment that you use in Lab 1. The most important part is this sensor here. So what this does is it puts out a little sound wave, a clicking noise that you're going to hear. And if there's some object in front of the sensor, it will reflect those sound waves back toward the sensor, and the sensor can figure out how far away the object is. And even better is it can do this in real time if the object is moving, which means we can use the sensor to make a graph of position versus time on the computer screen for that object that's moving. There's two parts to the experiment. In the first part, you're going to be pointing the sensor at a partner, and they're going to walk away and towards the sensor, and you'll make a graph of their motion on the screen. In the second part, you'll be attaching the sensor to the end of a track, and then studying the motion of a cart on that track. So we'll do that later. Now there's a few things you need to be aware of with regard to the sensor. First of all, there's two settings. So on the top of it, there is a narrow beam setting and a wide beam setting. The wide beam setting is better for pointing at your partner, so for people and objects like that. So put it on the wide beam setting to begin with, you'd point it at your partner, they'll walk away and towards the detector, and you'll capture their motion. For the track, it's better to use the narrow beam setting. So you'd put it to narrow beam, you'd clip it onto the end of the track, and then you do your experiment using the cart. But to begin with, you're going to start with it on the wide beam setting so you can measure your partner's motion. Another thing to be aware of is that the sensor has what's called a dead zone, meaning that any object that's within about 15 centimeters of the sensor, it can't accurately figure out how far away it is. So make sure whatever object you're measuring is at least 15 centimeters away from the detector, and as long as it is, then the sensor can measure objects up to a few meters away. And the third thing to be aware of is that the sensor can be fooled by objects that are nearby. So when you're pointing this at your partner, have them walk in the clear aisles between the desks, just so that the sensor isn't going to get confused by a nearby chair or person. Likewise, when you're using it on the track, just make sure that nobody's got an elbow or a book bag too close to the track. Try and keep the area nearby the track clear so the sensor doesn't get confused. So now I'm going to show you the velocity program that you're going to be using this week. So this is the desktop of the lab computer, and all of the programs that we're going to use this semester are housed in this Physics 1100 folder. So you look around on the desktop and find this Physics 1100 folder, open that up, and inside you'll find a whole bunch of programs in there loose, and also a few folders for those weeks when we need to use more than one program. This week we're going to be using this velocity program down at the bottom. So double-click to open that up. And once it's open, what you'll see is that there's a graph over here on the left, and also a data table over here on the right. So when we take measurements, the data gets graphed here on the graph. It will also show up as numbers in the data table. To take measurements, you just click on this Start button, and then you'll hear the sensor start to make that clicking noise, and then you can move your object back and forth, and you'll be able to see in real time what the position time graph of that object looks like. So I'm going to show you this now. I click on the Start button, and then I take my object and I move it towards the sensor and away from the sensor, and I can stop, and you can see in real time what was happening. If you want to take another graph, you just click the Start button again, and it's going to overwrite the graph that we already have. So I'll do that now. I'll click Start, and I'm going to take my cart on the track and actually move it right up close to the sensor. So I actually moved it right in until it's touched the sensor, but you'll notice that the graph went flatline at about 15 centimeters. And again, that's because of that dead zone. So the sensor can't measure anything accurately if it's too close. Now, in some cases, you may want to resize your axes. So if your data is all squished down at the bottom, for example, you may want to stretch it upwards. So I'm going to show you how you do that. But it's a bit of a complex procedure, so I've also put a handout up on the Moodle website so that you can refresh your memory. So to resize axes, what you do is you go up to the top and you click Display, Settings, and by default, you're going to be on the wrong tab, so you actually want to be on this Axis Settings tab. So I click on that, and you go down here to this Extras area, and you want to unselect Lock Origin Position and Lock Scaling. So you deselect both of those, then you click OK, and now if you want to resize your graph, if you hover your mouse over top of the numbers, so not the line, not the graph itself, but over top of the numbers on the axis, your mouse changes shape to sort of a squiggly double-headed arrow, and then you can click and drag upwards or downwards to stretch or squish your graph, and you can do that in both directions. You hover your mouse over top of the number, click and drag to stretch and squish things. If you want to move the whole graph around on the page, hover your mouse over top of the axis, so the line, not the numbers, and you can now drag the whole graph around. So if you needed to see the negative area, for example, that would be useful. So again, there's a handout on the website that shows you what to click to make sure that you can change the shape of your graph. When you're all done with the program, to close it, you just click the X in the corner. It will always ask you whether you want to save the changes. Always say no. So just say no to saving changes. Now, if you've already watched that video on how to take screen captures, then you'll already have seen a little bit of this. So in the first question of the lab, they ask you to measure your partner walking away from the sensor at a constant fast speed, and then you'd capture a graph of that with the program and paste a screen capture of the graph here. Then you'd do it again for a constant slow speed, put your other graph here, and then down here you'd want to talk about the similarities and differences between the two graphs. Specifically, you'd want to talk about how you know which one was the fast walk versus the slow walk. Then, on the next page, they ask you to make a prediction for what you'd see if your partner was walking to the left, towards the detector at a constant fast speed. What would that graph look like? So let's say that that's your prediction. So you draw it in, and then on the next page down, you're actually going to do that experiment. Your partner will walk towards the detector, and you'll capture that motion on the screen. Again, you'd screen capture your graph and paste it into your report. And then you'd want to compare the experimental graph to your prediction. So you want to talk about the similarities and differences. And to get full marks, you should talk about both the similarities and differences. So the differences might be the bumps and wiggles and curvature that you saw because your partner couldn't walk at exactly a constant speed. For the similarities, it's never enough to say your two graphs look the same. You have to be specific. So I recommend you use graphing language. So you could say, well, both graphs were linear and they both had a positive slope or a negative slope or zero slope. You could say both of them had a y-intercept that started above 0 rather than at 0. One thing you don't need to talk about, however, is whether the slope of this graph was the same as your predicted slope, because the prediction didn't have units, so in principle, we could assume it did have the same slope. So don't worry about it if your graph looks steeper or less steep than what you actually measured. Just talk about whether it was a positive, negative, zero slope, whether there was curvature, and things like that. So now we'll go back to the experimental apparatus, and we'll talk about what you do when you get to question 9. Now in step 9, things get a little more sophisticated. So you're going to be using the cart on the track and taking measurements of that. So the first thing you do is take your sensor and go to the narrow beam setting, and then you're going to want to clip this onto the end of the track, like that. The window of your sensor should be exactly vertical or maybe tilted slightly forward. That gives you the best results for getting data. And again, make sure that the area around your track is relatively clear of objects. Now, before you actually take data, you're going to want to level your track. And you do this every time you're using the track this semester. So you've been given a bubble level. And so what this is there's a little bubble and there's two lines. And when the bubble is in between the two lines, that means that the spirit level is level. So you're going to use this to level your track. You just put it on here and you check whether the bubble is in between the two lines as exactly as possible. If it's not, then down here at the end of the track, where you maybe have a little bit of trouble seeing it, this end of the track rests on the screw, and you can twist the screw to raise and lower this end of the track. So you do that until the track is nice and level. And then you can put your cart on the track. Now the motion that we want to capture for this part of the experiment is a slow exaggerated push and then a release. And we want it to be a slow exaggerated push because when you've got acceleration, which is what my finger is doing, I'm accelerating this cart when I'm pushing it, the position time graph should look like a curved line. So you want a slow exaggerated push so that you can actually see the curvature on the screen. If it looks like it kinked very sharply upwards, then you probably pushed a little too quickly. So go for a slow exaggerated push, and then you release it. And on the release, just make sure that it's going fast enough that it doesn't look like it's slowing down due to friction. So again, slow exaggerated push, fairly quick release. That's the motion you're trying to capture. Now, before you actually take your graph experimentally, you want to make a prediction of what your graph is going to look like. So just to give you some very mild hints, like I said, when my finger is on this, pushing it, I'm accelerating the cart. So that should look like a curved line on the position time graph. When I let go, It's now rolling freely, so it should be constant velocity, and constant velocity on a position time graph should look like a straight line. So think carefully about what the graph will look like from this motion, draw in your prediction, and then you'll do the experiment and compare what you actually saw to what you predicted you would see. Now, like before, if you've already watched that video on taking screen captures, then you've seen a little bit about what you do next with this. Is you're going to capture the graph of this motion on the screen, and then this week and this week only, we're going to make you do a hand-drawn graph. So you will screen capture your data table, paste that into your report, then you're going to make a hand-drawn graph, get an image of it using your webcam, and then that also gets pasted into your report. And then you're going to discuss things. So for example, you're going to calculate the slope of the rolling part of the motion, and you should be able to get the velocity of your cart from that. You're also going to talk about differences between your predicted graph and your real-world graph. So for example, on the real-world graph, instead of it being a totally linear graph, you may see a little bit of downward curvature due to friction. So that's not in your prediction, but you may see it in the real-world case. So be on the lookout for that and talk about it if you see it.